For those return viewers, welcome back. If you're a new viewer, then thanks for joining us. If you have not seen any of the other videos in the series, you may want to begin at the start, so here's the link. Looking at the YouTube stats, people are having an interest and watching the videos, which is great. But the stats also show that YouTube is only recommending the videos to a handful of people. Enter the evil YouTube algorithm. So if you've watched any of the episodes and have the mind to like, comment or subscribe, then please do, as this is what makes it possible for others to have the opportunity to see the videos too. So in this episode, we are building on the progress of the last episode where we buttoned up the motor, the EC and the related sensors. This time we'll be bringing to life the various sensors and start some testing and development with the blue pill and the TFT display. Well, let's get straight to it. So moving forward with the testing and development, I've tidied up all of this front end a little bit. The first thing I've done is I've mounted this power supply on the top here for the moment, just temporarily with a screw, because otherwise it's sort of in the way. Originally there's this big box here, which is the motor controller box, the old 90 volt DC motor that was originally in there. Obviously I'm not going to reuse that, and my plan is to mount this power supply on the front here in the position that this was originally here, this box. And so hopefully the power supply, well, I've placed it there and had a look. It fits pretty good. It doesn't protrude past this front point. I've also added for all of the motor controls this connector, this 9-pin D connector, which allows me to easily disconnect or connect whatever I'm working with. So on this line here is all of the motor control and sensing, so the control to the ESC, the motor speed pulses and the chuck speed pulses, and the motor room temperature information is all coming back here. So the next step is to get it onto this breadboard here, start looking at all of those four signals. And for the moment I'm still using a radio control receiver and transmitter because I haven't got myself a standalone PWM generator at the minute. And so I'll be taking a look at those signals on the scope, and just to give you a bit of an idea about what is where. It's a quick diagram basically. So this is fundamentally how it's going to come together. The 24 volt power supply, 1500 watt, and then I'm using a converter to get the 5 volts for powering the microcontroller and the control side of things, and the 24 volts goes directly to the ESC. So what we've actually got right now is this power supply, the 5 volt regulator, the ESC, the motor. This block here is effectively complete, and this is where I've added the connector here. And so the motor microcontroller control goes through that D9 connector into the control block, and obviously the control block then connects directly to the ESC, so it's just a pass-through connection. So that's what we'll be focusing on right now, is really tuning this up independent of the microcontroller for a little bit, and then I'll start adding the microcontroller and working through it. Additionally, there's also this display and control, so we'll have a TFT display, likely some buttons and a pot for controlling, directly controlling speed. Here I also have a control line going back to the power supply because my intention is to be able to monitor the current voltage. This also has 2 fans in it which are pretty noisy and they're going all of the time, so I'm going to monitor the temperature in here as well and control those fans so that they're only really running when they're required. It's pretty over-spec, this power supply, so I'm hoping that we can keep the fan noise down. Okay, so I've got it up and running now, and we're going to take a look at the speed first, so we'll see what sort of top speed we can get out of this. Alright, so let's kick it off. Firstly, you'll notice that it actually starts and operates pretty slow, and it has not enough torque, obviously. Yeah. I guess here. Yeah. I can't stall it at that speed. But obviously, if it's too slow, it's going to stall out, as you saw a second ago. So I have to be careful when I write the software for that to make sure it doesn't underspeed. Let's go to the top speed. Okay, so this is low gear. It's interesting to note here as well, I've added a couple of ferrite beads. I found that because of these long cable runs, there's a lot of noise and reflections occurring on these control lines, and it would make the ESC operate very unstably. So I've added this ESC on the test side here, which I've just wrapped twice. I've added this ferrite bead here on the test side. This one I had, and I've just wrapped the cables twice around here. And I also had a click-on ferrite bead, which I've just added to this side as well. And that solved the problem pretty quickly, so just a little note there on that. Let's look at the top speed. So the frequency is around about, so this is the pulse coming out of the back of the chuck here, the optical pulse, which is just a line tracer standard module I'm using. The pulse is pretty clean, which is nice, and it's got good peak-to-peak value, so I don't need any sort of treatment on that. And you'll see the speed is 18.3 hertz, and so it's 1 pulse per rotation on the chuck, and that's around about 1100 RPM. So it's a little bit lower than I was expecting, but it's possible this voltage can also be adjusted a little bit here, so I may consider to up the voltage a little bit to see if I can get it a bit higher. Theoretically it's 200 kV, so I think it was like 4800 RPM theoretical on the motor, but I'm actually seeing only around about 4000, so I'm not really sure. I also literally smoked the ESC that's in here. When I first turned it on, some smoke came out and made some noise, so I think it's a little bit broken, and that may be affecting the result. But I'm getting another replacement ESC for that soon, and we'll see if that has any change. Okay, hopefully that's in high gear now. Let's go again. And that's just cooking. And we're seeing around about 37.8 hertz on the main spindle. So 38 hertz is around about 2300 RPM top speed, and again that's a little bit lower than the original speed. Now the original speed is written here on the front cover here. It says it was up to 1500 for top speed here and 2900 here, as they have on the knob here. But in reality, I know it never did that. It was not getting anywhere near that sort of speed. The original motor itself is only a 4000 RPM motor, and the calculation says that you're not going to get 2900. So I expect actually even though I've upgraded to the brushless, I think the speed itself is probably about the same, which is a good result, I guess. But the low speed control seems a lot better. I mean, the whole speed control on this was terrible. Alright, so what I'm going to do now is I'm going to change this arrangement. So we're looking at the motor pulses. Okay, I'm going to change this so we're coupling on AC. Yes, we're doing AC and AC, and see if we can we'll move the trigger down a little bit here as well. See if we can get. Okay, so let's snapshot that for the minute so we can have a look at it. So the peak to peak here we're seeing on it is about 1.19, so I'm going to have to do some treatment on the signal and clean it up a bit. You'll also see this high frequency noise popping in here. I'm sure that given this is a pretty crappy oscilloscope, there's going to be a lot more of that, so we'll have to put a low pass filter on that to get rid of all of this high frequency noise, and also amp it up a bit. Now as far as the frequency goes, it's 475 hertz, which is the times that by 8. Yeah, so 3800 RPM on the nose for that. So as I said, the theoretical max is 4800, so quite a lot lower than the theoretical maximum. I'll have a fiddle with a few things and I'll clean up this signal. I'll put a circuit in to clean up the signal now, and I'll see if I can make any settings adjustments to the ESC to get a little bit more speed out of it, but I suspect that that's not going to happen. So continuing to work on the signal conditioning of the Hall effect sensor for the motor. The current signal coming out, so it looks something like this, right? It's only got a peak-to-peak value of a bit under a volt. You know, it's DC offset pretty high at 1.7, peaking up to about 2.6. Now, that's not going to work very well in a digital logic environment, so I need to clean that up. It's also got a lot of noise on it as well. So to clean it up, I come up with this circuit here, which is just a transistor. And before the transistor, I've got a bunch of diodes, which will drop about 0.5 volt per diode. And so it's really only conducting when it goes up and above that 2.5 volt peak. In any case, I fiddled around with the values for the gain of the transistor and came up with the 10K, 1K arrangement and these diodes. Then finally, I'm using a 74HC14 Schmidt type inverter to get the final clean logic output. And because I have that Schmidt inverter on there, I'm also using that to clean up the chuck speed sensor pulse as well. It's already pretty clean, so I don't really need it, but I've done that as well. So I've got it on the breadboard here right now, and as you can see, coming in here is the Hall effect sensor output, which is surprisingly crappy, but it's a linear Hall effect sensor, so it is what it is. And through the resistor and through the 5 diodes down into the transistor and on the output side there, and then routing those signals across to the 74HC14. Okay, so let's turn it on and take a look at what all this looks like. It's a bit noisy, so bear with me. So there's that Hall effect signal as we see it coming out. It's pretty consistent, and it's not as bad as I thought it was actually. It's relatively clean. The signal as I've shown it there. Here at the circuit point here, before it goes into the inverter, I'll give you a look at the signal so you can see what that looks like to compare. There's the output side there, just at the end of that resistor. And let's start it up again. So you can see that the shape is pretty good, and the peak heights are all pretty similar as well. So there are 8 magnets, and you know there's going to be a little bit of difference, I guess, with each of those magnets. But even so, I think it's consistent enough. And the diode transistor arrangement that I've set up has done a good job of giving a nice swing. So from 0 volt up to 1, 2, 3, 4, nearly up to the 5 volt peak consistently. So obviously that's going to go through the inverter fairly well. So let's have a look at that. And start her up. So I've stopped that screen there, but there you go. You can see that the signal is now a clean digital logic type signal, and we can use that to measure the speed of the motor itself. So I've just gone through and completed some testing to see what sort of performance we can get, and set up the ESC as well. So I thought I'd share that with you. So at the top here, this is the control pulse width, which I have tested is a valid range for this configuration so far. So from 1.1 millisecond is the dead stop, and then around about 1.685 milliseconds pulse width, and we're pretty much beyond peak speed at that time. And Futaba at least is running at 70 Hertz, so that's what I'll replicate. I did some settings down the bottom here for the ESC. 21 volt cutoff is what I configured Originally the setting for the throttle range was automatic, but I changed it to 1.1 to 1.8 milliseconds so that it would be definitive as opposed to something that might change. I changed it so that it had a hard brake, and that actually works quite well. It brings it to a stop pretty quickly. Clockwise was the default, and that's how I've left it. I changed the timing to 30-degree timing, and that's what's resulted in a little bit more speed here, which I'll describe in a minute. And there was a setting for PWM, and it doesn't really even say what the setting is for. I'm not sure if that's related to how it's pulsing the magnetic field or not, or whatever, but there was 8 kilohertz and 16 kilohertz, so more is better, and so I've changed it to 16, but I couldn't specifically see any great effect for that. I also cranked up the voltage just a little bit on the power supply. I don't think it really made much of a difference, but that's what it is. So the end result was, on the low speed, I was getting 20.5 hertz pulses out of the chuck, and that's equivalent to a 1230 RPM speed, so that's over 100 RPM up on what we were looking at before. And on the max speed, 42.5 hertz for the high speed, and 2550 RPM, which is a couple of hundred RPM more than we've seen before. And that's, I think at this speed we're really at, pretty much guaranteed to be at the original speed performance. So I got my development environment ready and set up. It's really the first thing you should do is make sure you get yourself a working and tested known environment. Now for my development, I'm going to be working with this blue pill, and this is a touchscreen TFT display, but I'm not going to use the touch. I'm probably going to use dedicated buttons. And as a first step, obviously make sure that I can program it, and I've done a little test here to make sure that the screen is working and I can start writing things to it. Now, I see a lot of people using serial and writing to the serial monitor within Arduino. Personally, I mean, I've never really worked that way. I like to have the status with the device, and it's a bit of a weird idea, but ultimately this is going to be functioning like this in any case, so I'd rather develop and display the results here as I'm developing, and probably avoid using the serial monitor. I might use it in some cases, but at this stage I think if you've got the display here, I can display it here, and that should be good enough. Now the TFT driver for this that I'm using is based upon the Adafruit one. And somebody made a modified library to work with the STM32, but the library, I think I messed around for hours trying to make it work. It was quite broken, there's something wrong with it. In any case, I took that basic library that was there and went through it and fixed it basically, and got it working. And it tests out fine now, and it's quite simple, so that's good. So that's what we'll be working with. So the temperature sensors are up and working. It went pretty smoothly, except for the fact that I forgot to actually connect power back to the sensors, and that was causing me a bit of a headache. I think I saw some other people have similar errors, but I wasn't actually powering the sensor. The sensor had a pull-up resistor with a 3.3 volts, and this sensor here, which is going to be the one that's going to be mounted inside the power supply, appeared to be working, but the sensor inside the case wasn't working. It was returning an error of 127 or something like that. 85, I think it was 85. Anyway, some weird number, and apparently that's an error code. And some other people had some things writing about it, so it sort of misled me a bit, because one was working, one was returning an error code, but the reality was that neither of them had power connected. It was just getting power back through the pull-up resistor and functioning. So it was confusing, that's for sure. Once I realized that the power wasn't connected, I cross-connected the power, and everything worked fine. Now you can see here both the sensors are working fine, one for the motor and one for the power supply. It's a single wire, so I only need one wire to connect to both of the sensors, and I used an address. So each of these sensors have their own individual addresses internally, actually, and there's a program you can get to extract that address, and so I'm explicitly now using the address so that there's no confusion. So if I heat up here, you'll see the temperature going up pretty quickly. 85 degrees. So I've set up this potentiometer here. We're using that to control the speed basically. And generating the pulse on the output here. It's a 70 Hertz pulse train, and the maximum width is around about 1.68 milliseconds, and the minimum is around about 1.1 milliseconds. And it's around about 3.3 volts, and so this is pretty much close as to what I was getting out of the Futaba receiver. To get good granularity in the control, I'm actually using the hardware timer type configuration, and then setting all of the detailed values for the width and the frequency, etc. So I'm not using this out of the box Arduino analog output, and that gives me the granularity because we're only talking about a very short end of the duty cycle. So at 70 Hertz, you really want to have more control over the duty cycle. Now, obviously, I could increase the frequency, but I'm not exactly sure if that's the right thing to do or not, and how the ESC would react to that. So I'm sticking to the standard 70 kilohertz, and that obviously means that the pulse width here is very narrow. So as I said before, to get the granularity in the control, I'm actually using the hardware timers, detailed controls, and that seems to work quite well. We can see here the ADC value is the value returned from the ADC from the potentiometer. The voltage is just a direct calculation from that, and the PWM is using the top and bottom value range. So the top range is 1684 microseconds pulse width, and the bottom end of the range is 1099. So actually I've had to lower this a little bit. Originally I had this at 1100 minimum, but once you get the value from the potentiometer, it's a little bit offset positive, and that seems to upset the ESC a little bit. So let's plug it in and see how it goes. That seems happy. To the brake. Seems to work quite well. So there you go. So far so good. So that's it for this episode. With some slow but steady progress, each of these steps let me confirm my assumptions, allowing me to firm up the final design. The next episode will focus on the power supply, adding some thermal management and a few other bits and pieces. So I hope to see you then.